Okay, I will start. So I want, in some sense, to sum up what was done. So we started with X, just some kind of nice topological space. And then we defined category of derived category. So T of X is derived category of sheaves on X, and define some functors, pi star, pi shriek, pi star, pi shriek, везде duality. Let's call this six-quadratic functor. I'm not sure what are six-quadratic functors, but and then we and they have some properties. So then we considered category subcategory here, which is complex algebraic varieties. More precisely, if you have a complex algebraic variety X, you consider space X analytic, space in usual topology, and consider D of X is derived category of constructible sheaves. So this is not purely topological notion. These are sheaves which are locally constant along some algebraic stratification. I want to say that today is the last day of the course, but I will continue on Tuesdays, and this will be organized by Dima. Precisely how I will continue. Just I want to give proofs of some basic facts, indicate proofs of some basic important themes which I mentioned in the lecture. No class on Thursdays, on Tuesdays. And you have again this six Grothendieck functors. And in this case, so far it was noticed that there is nice additional structure here, which is perverse structure. Perverse structure, which identifies some abelian subcategory perverse in T of X. It's some perverse abelian category. Abelian category. With many good properties. Good properties. And the only bad property it has is that it's pretty difficult to describe and to comprehend. That's something like, I would say, quantum mechanics. Something like quantum mechanics. It's important, clearly central thing, but to understand what you are doing is not so easy. And for instance, as far as I know, there is no direct definition of perverse sheaf on X, just without going through derived category and all this stuff.
So what is X here? X belongs
X, complex algebraic variety.
still complex.
Yes, complex algebraic variety. Okay, so now somewhere in 60s, Grothendieck, who worked on this here, realized that in fact this derived algebraic geometry, so there were no perverse sheaves, that has some additional structure, some kind of weight structure, it's not so easy to describe what it is. So, but let me just explain by example. So for instance, consider just P1. That's typical example. Consider P1, consider constant sheaf. X is equal to P1. Consider constant sheaf on P1. Consider projection X to point. And consider P star of constant sheaf. So this will be a complex which has so H naught of this is equal to C point and H2 of this is equal to constant sheaf on the point, and all other cohomologies are equal to 0. So the claim is that these things is in fact misleading. That these two sheaves are of completely different nature. They are isomorphic only because we don't see some additional structure which is in these sheaves.
What's your duality? I'm a bit confused. So
No, H2, we consider H2 of this thing. So it is just one-dimensional space. Okay.
it's not that they're unrelated. I mean, there is some relationship between these two sheaves. These are not randomly isomorphic.
Yes. So how do you express that they are not randomly? That's the claim is they are different. That in fact there is some additional. One can introduce some additional structure, so that this will have weight 2 and this will have weight 0. So it's not. And so. So it means that we see this category D of X, very nice category, but the claim is that this category is a shadow of some other category. So typical thing like this appears that if you have A is graded algebra, so you can consider category M of A of A models, and you consider category M graded of A, or graded A models. You have forgetful function. If you have graded A model, you can forget grading and get. But if you just work with these things, then you gradually start to realize that somehow there is some additional structure which is not easy. So if you just have this category, it's what you don't have algebra, you just have this category. What does it mean? This category of models or some graded algebra. In fact, I can tell some suggestions that if you have on this category, on algebra A, what does it mean that it's graded algebra? It means that you have action of C star on this algebra. If you have action of C star on this algebra, then you have action of C star on the category of models of this algebra. So, in some sense, to introduce, so I will say that this category is a shadow of this category. Suppose I just know only this category.
Without the action.
Yes. So I would like to express my intuitive feeling that it is a shadow of some. So one of ways is to say that there exists some concrete action of the group C star on this category.
Why C star and not just Z or something? Like you want okay, so can you
No,
explain
graded.
the action of C star?
So okay, let me explain. So what does it mean, graded vector space? The claim is that graded vector space is vector space together with action of C star. Z graded vector space is just this, nothing more, nothing less. I mean algebraic action, of course. So it's just okay. So once more, there are many situations in which we are working with some category, and then we realize that this category, in fact, is a shadow of some more precise category. And this is typical examples of the claim is that this category can be equipped with additional structure. And this additional structure, for instance, will separate this object and this object. These are two completely different objects in this category. Okay, and Grothendieck paper, which is called Standard Conjectures, which it's very, very closely related to theory of motives, such that if you prove these conjectures, then you will understand this new larger category. So once more, this claim is just looking at this category, you cannot see the structure. So the claim is that there exists some higher category which has this structure which is mapped to this by some forgetting of some structure. Okay, so Grothendieck wrote a short paper which is called Standard Conjectures, but not too much was achieved after this. So obviously something was achieved, namely in beginning of 70s, Deligne, so Deligne introduced this structure, weight structure, for varieties of a final field. FQ. So more precisely, in order to do this, first, what happened, of course, that first Grothendieck formulated, introduced corresponding theory for algebraic varieties or any algebraic closed fields that if X is algebraic variety over K, algebraically closed. Then you can introduce Ital d of X, is category of Ital Eliatic derived, constructible derived category. So, since all algebraic closed by Lefschetz principle, say all algebraic closed fields of characteristic zero are algebraically equivalent. Any statement which is correct in one case is automatically correct in other case. By some generalized principle, it's almost correct for any algebraically closed field. It's not quite correct, but most of statements. And so we introduce these things, we introduce these 6 functors. And you can study corresponding category and so on. And Deligne showed that in case when K is FQ star, FQ bar, that exists additional structure, namely every X defined over this field is defined in fact of some final field, some final field FQ. So you can consider now not just sheaves, but we consider Weil sheaves of Weil complexes. And this category Weil complex has, and he considered mixed on some special. Later on, I think it turned out that every Weil complex is in fact mixed, but it's, and so this gives some additional structure on this category. So this category of D mixed of X has more structure and has forgetful functor into D of X. And using this more structure, you can prove many statements. This is some kind of weight structure in this case. Now, in case
Does it satisfy what Grothendieck promised, or it's,
yes,
it is?
yes, in this case. So, so one of okay, so maybe I will comment on this. Yes, yes. So it does. From results by the linear, this follows, and in fact, more is false, more precise, as usual. It's not just general conjectures, some concrete things which give more information. In fact, okay, but then what's important is that in all these things, you also have this perverse structure. This structure. And again,
from perspective of Grothendieck's dream, we're supposed to be satisfied. We have the weight structure.
Yes,
answers
yes,
all
sure.
our
Yes. It answers, meaning that this intuitive idea that there is some additional information which, for instance, separates this to one-dimensional sheaves. This is done for finite field, was done by Delin. But important thing is that in all these things, when you have, essentially when you have secret factors, then you almost automatically have this perversity structure. And again, one of informal proofs that perversity structure is really important is that it turns out that it's very well compatible with this additional weight structure. Namely, that any irreducible perverse sheaf is pure, and any perverse sheaf has canonical filtration with respect to weight structure and so on. So it's ideally, in some sense, ideally fits with this structure. This, for instance, is, for me, is just proof. So say in the court of law, for me, this would complete proof that this is the correct object, that perverse category of perverse sheaves is the correct, so say, correct guy. Okay, and so now there are some statements about this weight filtration, which are also proved for complex numbers using different techniques. For instance, so for x over c, one can use Hodge theory, which is analytic, purely analytic thing. So it's completely different from what Delin has done. And so far, there's no, so say, Grothendieck statements are not proven, but some corollaries are proven. For instance, Hodge decomposition, and for instance, from Hodge decomposition, again, Delin, in his series of papers, he introduce the following series for any complex variety. You can introduce cohomology series H family of cohomology series, which depends on parameters PQ, which if you glue complex varieties, you have some exact sequences which relate this in standard way. And then you have the following series that if X is smooth projective variety, then this implies that HPQ n of X is equal to 0 if P plus Q is not equal to n. So for, in other words, for projective smooth varieties, you can compute these cohomologies if you know usual cohomologies of X. So sum of these things is equal to direct sum is equal to cohomology of X. Okay, I'm not sure the direct sum. Okay, so somehow cohomology of X are expressed for this thing. I don't remember now. But the idea is that you can, for projective smooth varieties, you can compute them if you know cohomologies, then you know these cohomologies. And the idea is that any algebraic variety is glued from affine varieties. That's, you know. But on the other hand, we can say that it is any affine variety you can compactify, so it's any variety is glued using resolution of singularities. For instance, is in some sense glued with pluses and minuses for projective smooth varieties. For projective smooth varieties, we can compute this thing. So hence, we can compute it for any variety. For example, if you just take earlier characteristic of these things, then you get collection of numbers to. So the claim is that for any x, you define collection of numbers x pq of x, chi pq of x, which is just sum minus 1 to the I dimension of hi pq of x. So just as usual, take a characteristic, and so these numbers are just invariants of. And they, if you cut, for instance, your variety in pieces, this thing will be additive, and so on. So this is all reflection, again, of existence of some weight structure, but it's just some kind of indication that it is there, but it's not the proof. So he didn't prove this by just using the fact that for smooth projective varieties you have Hodge decomposition. And then he just wrote some spectral sequences, whatever. It's just, he explains this purely technical thing, allows this.
Before you wait, so
Yes.
D of X, you explained, has this perverse D structure.
Yes.
And on the other hand, D mixed.
Also has perverse.
Now,
No.
my question is, I mean, could we somehow guess in some way, is there some good guess way, if we knew about D mixed, but we didn't know about its D structure, about this perverse D structure there, could we guess what is the perverse structure of D of X? What is kind of the relationship between the weights and the perversity, apart from the compatibility?
No,
Can we do reverse engineering somehow?
no, no. No, they're closely related, but they're different. It's two different structures. No, important thing about perverse structure was to realize that such thing exists. After you realize this, it's not that difficult to prove. All the things are.
So I'm trying to connect the two mysteries. First
Yeah.
of all, this growth-limiting structure, which is the weights, which exists.
Yes.
And then the T structure,
It's
And I don't
different.
think
These
they're
are different. They're different.
They're
So
incompatible.
just once more, when perverse sheaves appeared, it was completely unrelated to this thing. Then it turned out they fit precisely, but it was introduced for completely different reasons. So one of them was just this Gayeski-McPherson idea about intersection programmology, which should be self-dual, and another is relation with D models. And so you can, so this shows that there exists in this derived category, there exists some abelian subcategory which is much nicer than category of constructible sheaves. So this is, so they are called perverse sheaves, but in correct language, of course, constructible sheaves are perverse sheaves, and these are real sheaves in some sense. And then it was very soon realized that they ideally correspond to weight structure. So which is one of the proofs that they are really correct objects to consider. So once more, several people asked me, so what's the relation between perverse sheaves and constructible sheaves? So these are two different key structures, and the claim is that perverse is correct one and constructible is not correct one. But the only thing that with perverse is difficult because it is much more abstract. So
Can you repeat, please, about on this board you explained some facts about Hodge theory, and
yes.
I cannot mix it or.
No, this is
I'm still missing
no.
Sheaves here.
Okay. No, this is indication of the fact that the not just indication, but somehow in the claim is that over complex variety you have some remnants of this. You have proven, there is proven some remnants of this weight structure. It's not proven that it exists. So in principle, so the claim is that over algebraic variety, the claim not proven. So algebraic variety, this category D of X can be extended. It is a shadow of some nicer category which has some additional weight structure. So this is not proven, but some indications that it's correct are here. Okay, and also last time I also introduced, I think that's interesting thing is that you can define dg of x if you have x as G space. Then you can define category dg of x.
Maybe, I'm sorry, maybe another stupid question.
Mm-hmm.
These
Yeah.
mixed, you said for derived varieties, we don't know what it is, but
What?
for complex derived varieties.
Yes.
But certainly we know what we want to have over a point, over P1, so do we have,
Yes,
these
sure.
are well-known categories.
Yes. Here, there we do have, we understand. Okay, no, in fact, we understand more. I will describe. So, TG, covariant derived category. So essentially, this TG of x is just derived category of stack x mod g. So it's not algebraic variety, but this is x mod g is a stack. So the theory can be extended to stacks, and in the same way, if you have weight fixations, that it will be extended to this. Just so construction of this category is done just completely in terms of the usual category. So it's all structures which are in usual category will probably be inherited by this one. Okay, so now the claim is that Green's result about field and fine characteristic can be used in order to prove many results in characteristic zero. So for instance, suppose I have some result X in complex variety, and I have F as some element of Tx. Then what I can do, I can try to write down this complex variety. So this complex variety is, usually it is, for instance, quasi-projective. You can describe it by some finite number of constants in projective space. So hence, you can write that X is defined over Q of T1, Tn. And in fact, you can even say that it's defined over Z T1, Tn localized at some number m. So you invert finite number of primes. And hence you can consider now for any morphism, let's note this algebra by A, for any morphism A into F. So for this algebra, it's known that all its maximal ideals, quotients are finite fields. So for any morphism into some Fq, you get from X, you'll get variety XQ over FQ. And the claim is that for some Qs, for some, okay, let's note this rho. Let's note X rho. So instead of studying variety X, you can study collection of these varieties over finite fields. Now with F, it is a little bit more complicated because what is sheaf we don't know, but for some sheaves we do know. For instance, if you have constant sheaf, we have direct image of constant sheaf somewhere and so on. So there is a notion of sheaves of geometric origin, which is very simple. You just consider constant sheaves and then consider everything which you can get from them by all operations, all truncations, all. So the idea is that each of these operations is described by a finite number of constants. For instance, you have some y over x, you consider constant sheaf over y and consider this direct image. Then you say this y, again, is defined by some number of constants. So for almost all rho, you can define variety y rho over x rho. And direct image will be compatible with over, so you have here, you have y over x. For its direct image here will be compatible with direct image here again for almost all rho, and so on and so on. So if X is of geometric origin, then you can, so instead of studying varieties, sheaves and so on over complex numbers, you can study this family and you say that something is happening if it's happening almost everywhere. For some open set, whatever, one can define this. And in particular, things, but here you can already use, so let me see that if I have sheaf if I have sheaf F rho over sheaf complex sheaf over X rho, which defined over field F Q of rho, then I can consider corresponding variety X rho bar over algebraically closed field, and I consider F row as veil sheaf. And it automatically will be mixed. And hence, to this sheaf, you can apply this weight filtration and prove different theorems. So, for instance, one of the theorems which is proven this way is decomposition theorem. So, decomposition. That if pi x y proper morphism of algebraic varieties over C, for example, and F is irreducible perverse sheaf of geometric origin. On X, then its direct image F is completely reducible. And so the proof is that you take this sheaf, you translate it into this F row, and then you see that for almost all the rows, it will be again irreducible perverse sheaf, perverse veil sheaf. Using weight filtration, you prove that it's completely irreducible, that its direct image completely irreducible. Direct image corresponds to this direct image, and this implies that this is completely irreducible. So why this theorem is important? Because very many results about sheaves over C, which you can prove using going to positive characteristic and using this weight filtration by Deligne, you can in fact prove by just referring to this decomposition theorem. So it's somehow allows you to avoid going to positive characteristic and just refer to this result. No, also this result is very convenient in itself. Again, this result is reflection of this weight structure, which is not proven yet. So okay, so now so we have this suppose we have C of x, 6 cognitive functors.
Structure, then we can erase this geometric origin and get it in full generality.
No. See, it depends on whether this is geometric structure. Nobody told you that. Let's put it by example of graded thing. Suppose you have a graded thing and you have some modular weight. Nobody told you that there exists a graded model which will map to this model. So just a priori, I don't see any reason why it should be. So, but if my model is an image of graded model, then everything will be okay. All things geometric origin by definition are of this type. So So the idea is that if such thing exists, then you will just say that I don't want to consider this sheaf. It has no geometric meaning whatsoever, because it's clearly not, has nothing to do with geometry. It's just artificial construction. So why should prove anything about this sheaf? Okay, I don't know whether this kind of things is correct or not. So we have these 6 quadratic factors. Just what I wanted to say. So I want to say that it is better to try to express everything in terms of these factors. For example, if you have 2 things, so what is home FH? So I told that this is so this is some kind of new factor, but so it's, in fact it can be written. We can take d of f, tensor, consider tensor sheaf of h, which is expressed for usual factors. Then consider pi star by p star to the point. Let's denote this home fh. This lies in the right category of point. So this is what Ethan proposed to call enhanced home. So if you have 2 sheaves fx, fh on in d of x, we construct enhanced home, which is objects in the right category of a point. And then you can read off usual home as some kind of zero homology of this, something very simple. And similarly for okay, and there is one, so I didn't have time, I just want to mention there is one factor which is not expressed for these factors, which is very close to this, but not expressed, which is called nearby cycles, specialization cycle, nearby cycles, vanishing cycle, and so on. So that if you have x into a1, and you have sheaf f, then you can take x naught equal f minus 1 of 0, x star is equal x minus x naught. So if f is in the right category, d of x star, then you can define factor, so from d of x star to d of x naught, in fact with some, here you have some additional operator, and it's called monodromy operator. So which is very important factor, which just tells the following, that you take x epsilon is equal to p minus 1 of epsilon, and you consider your sheaf f restricted to x epsilon, and then you consider limit when epsilon goes to 0. And so this can be defined. It's not trivial thing, but important to see that it is not expressed in terms of these previous factors. So it's a little bit, just a little bit more sophisticated. And it also has some very important properties. For instance, it maps perverse sheaves into perverse sheaves. Maybe I have to shift by 1. And So it's defined only in this, in one-dimensional situation. There were some attempts to define this for high dimension, but not very successful. So this functor also has important application. So I didn't have time to describe it. So. Yes. What?
You're missing the limit part.
No, I missed something. And from what reason there, it's not clear what psi is. So,
so we have collection of Sheaves F on X epsilon. You can always assume that X is equal to Y times A1. There is no problem. That's okay. So you can consider this Sheaves on X, and then the idea that you want to consider limit of this. So X naught is equal limit when epsilon goes to 0 to of F epsilon. This is F epsilon. For instance, derive category of X. Whatever. Consider limit, but it's not so easy to describe what does it mean to have this limit. But just I want to mention that there is this functor and this companion functor nearby cycles. This means that some cosmologies of epsilon which are
psi is this.
next term. Yes, it's psi. Not X naught, F naught. So psi of F is equal limit of F epsilon. So this can be described, but it requires some. Maybe I will do it later, but and again, this functor is good. It preserves perverse structure. So this is one more proof that. So this functor was defined long before perverse things. This is one more proof that perverse is correct thing. So this functor is exact. Perverse exact maps perverse Sheaves to perverse Sheaves. It's compatible with duality, and it's related to other functors, but it cannot be expressed. So other functors, it is some additional. In many cases, in fact, it can be expressed, but in general, it is a little bit more. It gives a little bit more information. Also, it's compatible with weight filtration. It's very nice functor.
And there is Fourier transform.
Yes, it is very much related to Fourier transform also. Yes, there is Fourier transform, but Fourier transform, it's so Fourier transform exists, for instance, over finite field. Over complex numbers, it doesn't quite exist, because Fourier transform, it's easy to translate into the language of D models, and for D models, it might map D model into regular singular Z model into not regular singular Z model. For instance, if you take, for instance, line and consider delta function at point lambda, then its Fourier transform will be, if lambda is not equal to 0, its Fourier transform will be not regular singular Z model. So hence, over complex numbers, there is no. In our direct categories, there is no Fourier transform. So it's no. This is also something which is not quite understood. That's, for instance, Nick Katz, he made a lot of computations and so on of estimating some weights, using weight technology, estimating some variety of sums, so on, and he used all the time Fourier transform, and he tried to formalize what does it mean to have the Fourier transform. You have 6 quadratic factors, you have Grothendieck Fouillet as well, he just wanted to axiomatized in some sense the situation. He has some axiomatization and suggested that it should be work for complex numbers or FQ and so on. So, but somehow it's more ideology than precise statements. So once more, he has a lot of concrete results which he proved some, but he tried to express general scheme, and he has a paper in Bulletin where he describes this general approach, but there's no formal definition. No, you're correct. There is this additional thing. Okay, so that's okay. So the idea is that there are many problems which can be used to the study of sheaves or complexes of sheaves on algebraic varieties, and if you would know the weight structure, then it would be much easier to prove many non-trivial properties. We don't know this, but we do know this in finite fields, so there is some trick how to, if you want to prove something, you could go to finite fields, use it, and go back. And in this way, you get some highly non-trivial results. But I should say in general that somehow I have some impression that in algebraic geometry there are two kinds of results. Some first level results, which are quite non-trivial, for instance, Riemann Roch and so on. And the second results, which are related in some way to this weight structure, for instance, Hodge decomposition, which has several different postulates. There is proof which goes, I think, the ring can be proven, proof which by analytic methods, and there is the Green-Rizzi proof which uses periodic deformation. But generally, somehow, the results of this second level, they're much more precise and much more difficult. So this second layer on algebraic geometry, which is difficult to access. So there are some points where something is done, but the general situation is not understood.
If you're allowed to stay here for more, can you say
Yes.
this weight story you mentioned, the motives? So how does that fit in this?
No, so okay. The idea is that motives should represent. The idea of motives is that it represents any cohomology kind of theory which is on varieties, in particular weight. If there exists weights, so if you have a theory of motives, correct theory of motives, it automatically will include weight thing because it covers everything. So the idea is that we are working with sheaves, but in some sense, Grothendieck's idea was that all sheaves, the only interesting sheaves are of geometric origin. So everything, in fact, comes from varieties. But then you consider direct image and so on. So in this way, so everything comes from motives. In particular, these motives have to have this weight structure, because if you assume that this weight structure exists, then it is already hidden in these motives. So essentially, this weight structure tells you that some morphisms a priori are possible, in fact, are impossible. For instance, this two one-dimensional space, two one-dimensional space. Why not to consider morphism between them? But the claim is that in the real world there are no morphisms because one has weight 2, another has weight 0. you just don't see it, but it doesn't mean that. Okay, so I think that it's.